The company Affymetrix has a specific normalization procedure in their software. After hybridization, Affymetrix gene chips are scanned and the resulting pixel level intensities are stored in a DAT file. Then the Affymetrix gene chip operating software calculates probe level expression as the 75th percentile of the interior pixels for each probe, and these results are provided in cell files. Therefore, a cell file stores one value for each perfect match and mismatch on the entire gene chip. Normalization may be applied to the probe cell intensities prior to calculating probe set signal or may be applied to the probe set summaries. Since only one sample is hybridized to a given gene chip, normalization methods for Affymetrix gene chips involve two or more gene chips. First, one must choose a baseline gene chip against which all other gene chips are normalized. Normalization then proceeds as follows. First, the 2% trim mean expression is calculated for the baseline gene chip, and that is represented by x tilde base. Second, the 2% trim mean expression is calculated for the kth gene chip and is represented by x tilde k. The scaling factor is then taken to be beta sub k, so that the scaled values for probe sets j on gene chip k are given by this equation. For Affymetrix gene chip data, only one sample is hybridized to a gene chip. Hence, the MA plot is useful to normalize between two replicate gene chips. The MA plot consists of plotting for each probe j for gene chips I and k, M versus A. Again, under ideal circumstances, these MA plots should show a cloud of points about 0 for technical replicates. If intensity-dependent normalization is needed, a Loess regression can be fit to the MA plot. The fitted values from the Loess regression are then used to adjust the data, such as what we saw with custom spotted arrays. However, since we would like to analyze the data using the normalized probe intensities per gene chip, rather than the normalized log ratio of intensities for a pair of gene chips, the normalized chip intensities are given by these equations. For probes J on gene chips I and K. Again, this adjustment is apportioned equally to both arrays when considering the correction on the original scale. To normalize more than two gene chips, the method is extended to look at all distinct pairwise combinations, recording the pairwise adjustments. The normalizations are carried out in a pairwise manner, and the adjustment for each gene chip is saved. After estimating the adjustment for all pairs to an array, the adjustments are equally weighted and applied. This will result in a set of adjustments that can be applied to the entire set of gene chips. Rather than using all genes for normalization, one may want to restrict the set of genes used for normalization by identifying those that are invariant. That is, perhaps the normalization relation should be based on non-differentially expressed genes. Since it is unknown which genes are non-differentially expressed, a heuristic method was developed for identifying an invariant set by Li and Wang in 2001 and was implemented in the D-chip software. Specifically, the invariant set method works by normalizing all arrays except the baseline array to a common baseline array having median overall brightness. The underlying assumption is that a probe belonging to a probe set that is not differentially expressed should have similarly ranked intensity values across all gene chips. One of the best ways to compare the distribution of a sample X with a known parametric distribution is to use a quantile plot. The normal quantile plot is the best known example, and we discussed the use of the normal quantile plot as a way to check the normality assumption for a linear regression model. As a reminder, a normal quantile plot consists of a plot of the ordered values in your data versus the corresponding quantiles from the standard normal distribution. If the plot is fairly linear, your data are reasonably Gaussian or normally distributed. Otherwise, they are not. Quantile normalization, which is now the most commonly applied normalization method, assumes there is an underlying common distribution of intensities across gene chips. A QQ plot can be used to compare if two gene chips come from the same distribution. If so, the points will fall along the diagonal. To carry out quantile normalization for n gene chips, first let X represent a matrix with n columns representing samples, where each sample is in one column, and G rows, where each row represents a probe, that is, a perfect match or mismatch. Sort each column X and define the sorted matrix as X sort. Keep track of the original order along with the sorted order. Then take the average of the quantile in a particular row and then substitute this value in for each of the individual elements in that row. Finally, get X norm by rearranging each column of X prime sort to have the same ordering as the original X matrix. Let's look at a very small example to illustrate quantile normalization. We have the X matrix for some probes from an Affymetrix gene chip. In the row, we have probes. In this example, there are 20, whereas samples are in these columns. We need to keep track of the original order for each column, so those are added here. When performing quantile normalization, we start by sorting each column in X and define the sorted matrix as X sort. In this example, each of the 4 arrays have been sorted. Notice we are keeping track of the original order along with the sorted order. Next, we calculate the average of each row in X sort. Then, we substitute the row average value into each of the individual elements in that row to get X prime sort. To obtain the normalized matrix, we rearrange each column of X prime sort to have the same ordering as the original matrix. In the active learning lab associated with this module, you will practice reading in Affymetrix gene chip data, extract perfect match and mismatch intensity values, and perform cyclic Lewis and quantile normalization.